Swayam Prabha. Digital India. Educated India.
This is the other interesting property, and using this coding becomes much easier. You know the partition is quite simple. You know which node will go into which partition, right? When I code it, it becomes easy. I know, okay, take this label, if the label is label modulo 2 is 0, I do this and then I process it to the next node, modulo 1 it will be, so modulo 2 will be 1, so I can just process it like that, right? So the equipartiteness is one interesting property. Both the partitions have equal number of vertices, and then n regular, this we have seen, and diameter is n on 2 power n nodes. Okay, so everywhere we are in 2 power n nodes, but we are talking in terms of the power n, which is a log factor, right. Not only diameter is n, connectivity is also n, vertex connectivity and edge connectivity, if you see, both are n here. Okay. So you have to remove at least n nodes to disconnect the graph. And it is also pancyclic, even pancyclic, they call it bipancyclic, that is there are cycles, even cycles of every order from 4 to 2 power n exists in the graph. You can get cycles, like suppose I just go back, I will just show you that. In this graph, if you want to look for a 4 cycle, it is immediate, right, all the inner cubes at least you can immediately see that there is a 4 cycle. You can also find a 6 cycle, 8 cycle, 10 cycle, 12, 14, 16. So, all possible even numbered cycles exist in the graph, right. So, you can think of this, it is a very good exercise. In fact, you can also construct these cycles using the vertex labels. That is again coding, from coding perspective, I can give you the cycles using the labelings itself. If I want a 6 cycle, I know where to tweak my label to get a 6 cycle out of it. If I am giving you a starting and end node, if I want to connect a path to it, I can give you. Just by looking at the labels of the vertices, I can say what will be the shortest path between the two labels, two nodes. And if I want a cycle, how containing these two vertices, that also I can try to construct it. Right. So these are some interesting properties. Since we have said there is a k cycle of order 2 power n, there is a Hamilton cycle, right. It is Hamiltonian connected. In fact, it is Hamiltonian connected also. You take any two vertices in different partition, you will be able to get a Hamiltonian path connecting the two vertices. One vertex from partition 1 and any other vertex from partition 2, you pull out, you will be able to find a Hamiltonian path connecting these two. It is called as Hamiltonian connectedness. So that is another beauty of this network. And then comes some interesting algebraic properties. Okay. So when I say vertex symmetry, what I mean is that given a hypercube, okay, there is an automorphism between any vertex I take, I can find a mapping, I can find an automorphism. Okay. So by automorphism what we mean? Suppose I give you the hypercube network, that is my Qn is my say group G, if you talk about in terms of group language. An isomorphism or an automorphism, it is nothing but a mapping from G to itself such that some property is satisfied, right. So here our isomorphism property is nothing but if there is an edge in my first graph, my host graph should also have an edge connecting the mapped vertex. UV is an edge, then f of u, f of v should also be an edge. That is the isomorphism property we are looking for. Since we are talking about Qn to Qn itself, it becomes an automorphism. Okay. In fact, it is vertex symmetry. Any node I take, I can map it to any other node in my network, such that the structure is maintained. Okay. There is a mapping which will take this node and map it to some other node in the network, and it preserves the adjacency. Okay. So that is one thing. Not only it is not only vertex symmetry, I can also talk about edge symmetry. Given any edge in my graph, two edges, I can always find a mapping that connects, such the mapping preserves adjacency. Okay. Not only edge, I can even extend edge to P3. Okay. So a path on 3 vertices. Okay. It is a P3 symmetry is also existing. You take any 3 vertex that are connected by a path, okay, and you give me any other P3 in the same graph, I'll be able to give you an automorphism map which takes the first vertex to the first vertex there, and all the 3 vertices are getting mapped correspondingly, and the adjacency of the whole network is also preserved. Okay. And here we cannot talk about P4 symmetry, because we know you take a 4 vertex, there is a possibility of a cycle forming in, right. So, we cannot take a P4 and map it to a C4. Right. If suppose I look at a P4, induced P4, right, there is no cycle that this 4 is going to form, but there is a possibility that I could map it to C4. So, in that sense we do not talk about P4 embedding, but it is C4 symmetric. If I take any C4, a cycle on 4 vertex, I can map it to any other cycle on 4 vertex. Right. So, these are some interesting properties which we will be using to embed any subgraph, any element in, any host or guest graph into my host, when host is my hypercube. Okay. So, there are some special terminologies which we will be using for a couple of minutes. If G is a subgraph of a m-dimensional hypercube, then I say G is a cubical graph. Okay. That means like it sits inside a cube graph. So, just to mean that we just say it's if it is a subgraph, then I call G to be cubical. So, we will also try to look into these kind of embedding. When we are trying to embed, we want to embed it in the best possible hypercube. Given a graph, if I want to embed it into a best possible hypercube, what are the conditions that I should look? The number of vertices in my graph should be matching at least, right, in my hypercube. So, to catch up with that, we have certain terminologies. If n is the smallest integer, which is greater than number of vertices in my given graph G, then I call Qn to be optimal hypercube. So, that I want to see whether G is sitting as a subgraph in Qn or not, and if it is not in Qn, can I check at least in Qn plus 1, can I leverage myself, go to higher dimension, 1 dimension more, can I go and check whether it is sitting there as a subgraph. Okay. So, these kind of questions were interesting to answer and look for. So, what is the condition for a graph G to be a subgraph of hypercube? You have seen all these properties, right. So, all those things should be satisfied, at least necessary condition, minimum those things should be satisfied for us. Not all are sufficient, if it is satisfying, then we are happy about it. So, minimum thing is our given graph should be bipartite, right. If the given graph is non-bipartite, obviously it is not going to be a subgraph of my hypercube, which is a bipartite graph, right. So, G should be bipartite graph such that when I look at the partition, my partition should contain at least less than or equal to 2 power n minus 1, right, because I know my hypercube contains 2 power n minus 1 vertices in both the partitions. So, this condition is also something interesting to see. Simple condition for trees and all, it is going to be a very trivial condition. If it does not satisfy this, I can just throw the network outside, right, I can immediately say and the max degree should be at most n. These are some simple conditions that we check for immediately to check whether G is a subgraph of Qn or not. These 3 conditions is what I will look for immediately, and then we will go into higher order tests. If these are satisfied, then I have to go check whether I will be able to give you an embedding or not, right, give you a mapping which will take it over there or not. Right. So, coming to cubical graphs, there is certain results which are like age old, as I told you, from 1970s people, even 1960s people work. Okay. Any cubical, for any cubical graph G on P vertices, the cubical dimension, okay, where it is going to sit as a subgraph, okay, the cubical dimension is going to lie between P minus 1, log P and P minus 1. Okay. On P vertex, if I am looking at, then it can sit. I am not restricting which cube it is going to sit in. I am not talking about optimal hypercube, but where it is going to sit as a subgraph. If you look at that dimension, that is what cubical dimension is, that lies in this range, that dimension lies in log P to P minus 1. Okay. So, this was one of the very first results when people started talking about cubical graphs. and you guys must have heard these names, Gary and Graham. They are famous people in this computer architecture and parallel computing studies. And there is also another improvement. Cubical dimension is less than or equal to 2 times p minus 1 by 3, 2/3 of p minus 1. Okay. So, for the first case, you might be wondering how did this range come into picture, right? It is a huge range, log p to p minus 1, right. What can we say about this? Why should it be log p or log p minus 1 given any graph G? I know it is a subgraph of some hypercube, right. So, can you think of a graph whose dimension will be p minus 1? Think of a path on p vertices, pp, right, or p 2 power p I should say. Path on 2p, already we are talking about p vertices. So, it would go into log p here, right, because we know 2 power log p has Hamiltonian path and its length is going to be p, right. So, one end will be nothing but the path graph. For the other end, think of a star graph. There is one center vertex and you have p minus 1 pendant vertices, a star, right. So, star, because you know the degree of star is going to be p minus 1, I need my cube to have p minus 1 degree, right. So, therefore, cubical dimension will be forced to be p minus 1 over here. So, there are graphs which attain these bounds also, and there are also other improvements that has been done when my minimum degree is 2. So, star graphs and path graphs are now ruled out. So, if I look at minimum degree 2, that means what? I am not talking about a tree anymore, right. So, in that case my cubical dimension has been improved to 2/3 of p minus 1. Okay. So, these are some improvements, people keep working, and why they did all these work? Because they wanted to do an embedding, they wanted to write an algorithm which would take a corresponding graph, look at its number of vertices and dimension, and it will go and find a mapping in corresponding hypercube, okay, so that they can run the program, execute the program and so on. Right. So, another about complexity, if I give you any arbitrary undirected graph, okay, with say maximum degree just 4, at most 4, okay. Even if I give you such a graph, it is NP complete to decide whether this graph will sit as a subgraph in any hypercube. Okay. So, this problem is again NP complete to decide whether a graph G is cubical or not. Okay. A simple, even for degree 4, degree 3 we can do it easily. So, degree 4 it is a little complicated, and similarly to find a cubical dimension. Okay. First of all, to check whether it is going to sit inside some hypercube as a subgraph, that is difficult. If at all I tell you yes it is cubical, then to find that cubical dimension, in which hypercube will it sit as a subgraph, to find that is also again NP complete. So, somewhere we are bowled here, stumped, done. So, we feel like okay, what is there to do then, I do not have anything to do here, right. Yeah, but people are there, they always find a way to bypass, right. So, people then entered into okay, I do not want any arbitrary graph, I know it is NP complete, let me not go into that difficult task. I am bothered about algorithmic graph, and my algorithmic graphs most of the time are trees. So, let me look at trees, try to embed trees, whether is it at least embeddable. Again comes Wagner and Cornell, they are again there to always put us down. Given a tree T and in any integer n, it is in NP complete to decide if T is a subgraph of Qn. Given n and the tree T, to decide whether this tree is a subgraph of Qn, it is NP complete again. Okay. So, again they take all the credit, and they have shown this for k greater than or equal to 3 and n, to find the complexity of the problem of embedding tree with the maximum degree k into Qn. This is still, people are working in this direction when the maximum degree is 3. 3 or 4, like you fix the maximum degree of my tree, then to talk about it, there are lots of results in this direction. So, when I say k equal to 3, I am boiling down myself to a binary tree. Right? Even for k equal to 3, the problems have been shown to be lot of difficulties are there for any general binary tree. Forget about any tree. We first started with arbitrary graph, then we came down to trees. Even in tree, I can't handle big trees. Let me go down to binary trees. Arbitrary binary trees. Is there any result here? Not all binary trees, we don't have any result again there. Only that if any binary tree with bipartition, it has this many vertices, then we can say that it is a subgraph of Qn. And this was relaxed. We are like giving a very loose terminology here, mod x less than or equal to 2 power n minus 1, mod y less than or equal to 2 power n minus 1. Maybe the bound is too large. I might not have even those many vertices in the graph. Still I am giving you for some n, if this is true, I can say okay, this is embeddable. Okay. But if I want to talk about a tight bound, why should I waste resource if I know I have only an 7 vertex node, binary tree say on 8 vertex, why should I embed it in a 32 node hypercube? I am literally wasting from 8 to 32, right? Almost 4 times I am wasting the resource. So, can I do it in my optimal hypercube? If I am talking about an 8 node binary tree, can I put it into a 8 node hypercube? Right? So, that problem was also kind of solved, but not for subgraph. It need not be a subgraph. So, it was proved that with dilation at most 2, that is every edge is mapped to a path of length 2, at most 2. Either edge goes to edge or edge goes to a path of length 2. So, this was shown. So, as a result, in optimal hypercube I know it is of dilation 2. So, that means what? Next to optimal hypercube, an 8 node graph, if it does not sit inside an 8 node hypercube as a subgraph, I know it will sit inside a 16 node hypercube. So, I can go 1 dimension more instead of going 4, 5, 10 dimensions, I can at least talk about optimal and next to optimal hypercube. So, this was also proved. So, I have just given the corresponding authors whoever have proved this. So, any binary tree is a subgraph of its next to optimal hypercube. So, again comes a bigger question. If suppose I have a tight bound, I give you my n lies in this range, I have a binary tree on this many nodes. This can be embedded into Qn with load 1 and every other parameter bounded by a constant. Okay. So, these binary trees as we go, you might look what you said just now, you gave a result about binary tree that it is embeddable into this. These come along with this criteria here, right. So, when we go into the generic case, we do not know about the degree, it could be too large. Okay. I am not giving you any restriction on degree here, right. On n nodes only I am saying, where n lies between 2 power n minus 1 and 2 power n. So, these are like some kind of higher order problems which were solved. And after this also people were working, even I had worked in this related problems, trying to embed different classes of trees, okay, relevant to whatever problem we were doing. So, this problem of embedding in hypercube is kind of existing even now. The only thing is like many people have moved out of this because they cannot solve it anymore. That is one big difficulty, because it is already shown to be NP complete for in many of the cases. So, they went into approximation algorithms or how we can give other types of embeddability possible. Okay. Instead of going in for subgraph embedding or dilation 2 embedding, load 1 dilation 2 is what we opt ideal case we are looking for. Even if it is not there, then they go in for higher order relaxations. Right. So, this is about hypercubes, and next about generalized hypercubes. So, if you look at the hypercubes what we were talking about, there we had only 2 digits, right, binary 0 and 1, we were talking about binary hypercube. So, there were generalizations Why I should use only 0 and 1? I will go up to base b for some b greater than 1, 0, 1, 2, 0, 1, 2, 3, 4, 5, I can use as many digits. So, there were different kinds of definitions. So, I start with a complete graph on b vertex. See, if you look at binary cube, I started with a k2, right, and we can construct it over Cartesian product of k2. So, people thought of why only k2, I will take a k3 or k4, a complete graph on 4 vertex, and let me expand it, blow it up in higher orders, right. So, when b is equal to 2, we get our binary hypercube, otherwise it is a higher order hypercube. This is one kind of generalization. There were also other kind of generalization. Instead of taking kb, you could have taken a cycle on b vertex, that is also a possibility, right. So, there are different definitions, different kinds of generalization that is possible. So, officially to define in similar language of our binary hypercube, you look at any n bit string where the bits are going to lie between 0 to b minus 1, okay. And you say that two vertices are adjacent if and only if they differ in exactly 1 bit position. We do not bother about by how much it differs, but at least exactly in 1 bit it has to be differing. All the other n minus 1 bits are same, only in 1 bit they differ. Say for example, when I go for ternary cubes, when b is equal to 3. So, I go for the label 0, 1 and 2. So, this is q1 3, the base case, a triangle k3, right. And if I try to extend this, this is going to be my torus q1 3 cross q1 3, or you can just see the labels how it goes. 0 0 is adjacent to 2 0 because they differ in exactly 1 bit position, right. So, this is another direction of study. These were also called as Hamming cubes, okay, because it is named after Hamming, because we are using all the Hamming codes. The way we talk about these binary labels and their differences, even we will be using the same to identify a path or a cycle, all those things that I was telling you about, those are based on Hamming codes. Okay. So, these cubes were also called as Hamming cubes in honor of him. Okay. So, what are the properties? Interesting property is that Qn has b power n vertices, a b base cube if I talk about, and it contains these many edges. So, in hypercube we know it has 2 power n vertices and n into 2 power n minus 1 edges, right. We had two partition that was possible, independent set of size 2 power n minus 1 on either side, and every vertex had degree n, right. So, it is n into 2 power n minus 1 number of edges. So, here a similar extension you can see, it is n into b minus 1 into b power n edges, half of that. And it is also regular, it is a regular graph with a degree b minus 1 into n, and diameter is again n. Even though we are talking about b power n vertex, 3 power n, 4 power n, we boil down to log base b. Okay, so, we will just reduce everything to log base of that, right. Similarly, it is Hamiltonian, same property, that is why it is called as generalized hypercube, it's everything carries over in base b also. So, there is a k cycle for every k. In hypercube we know it does not contain odd cycles, it was bipartite. Here we do not have that condition, because we started with a k3. If you look at the example, we start with a triangle, right. So, triangle is going to sit in every cube that is formed inside that. So, at least there is a 3 cycle. In fact, not only 3 cycle, it contains every cycle of any order you take, 3 to b power n. Okay, so, you can find a cycle and again it is vertex symmetric and edge symmetric. So, these are all algebraic properties. Using these again, these networks are again coming back into structure. So, we are trying to, when we talk about scale free networks, these are scale networks, these are scalable, right. So, when I say scalable, I mean when I increase my n from some 10 dimension to 11 dimension, I can easily extend this, expand this, right. So, scalable networks have their own cost, but still we know how to connect, how to get a higher dimensional cube from lower dimensional cubes, right. Nowadays, what we look at complex networks, they are scale free networks. We cannot scale them obviously, and they do not have any such kind of structures. Okay. So, these structures are also like, they also have algebraic backup, that you can define a very rich algebraic structure on them and talk about all algebraic properties on these networks. That is also another direction completely where work is going on still. Okay. So, with this I think I am done already. So, I do not have time to talk about Kelly graphs. So, one example of Kelly graph is hypercube and generalized hypercubes. These are all examples of Kelly graphs. Okay. Like what is Kelly graph is, given a group. So, that is what I was trying to tell you. We can talk about algebraic structures on these networks. So, given a group and a generator set to generate every element of the group, I can use that property and I can construct my network, okay, using the generator set. Okay. So, Kelly graphs have very rich structure. You can see these are all examples: hypercubes, generalized hypercubes, torus, mesh is also a Cartesian product we can have. So, like this, lots of structures are there where we can bring in our algebraic properties to explore the network. And coming back to our spectral properties, hypercubes of dimension 3 is completely determinable through its spectral values. Again, for n greater than 4, problem is open. I cannot determine the structure just by looking at the spectral values. For some cubes it is possible. There is a pattern for the spectral values of hypercubes. So, if you look into that, and we can try to decide, okay, is this a hypercube of order say 10, that means that already I have to look into 2 power 10 spectral values, right. When I am talking about dimension 10, we are in large scale. So, determining hypercubes through spectral values is still open. For 3 and 4 they have studied, the study has been done, but for higher dimensions it is still open. At least spectral values we can talk about. These graphs, nobody has explored it in that direction, the algebraic aspects. Other than being a Kelly graph, it is kind of open still. Okay, so, the arena is open. If you think of this as interconnection network, it is fine. If you think of it as a very special class of graphs, you can still do a lot of work in this direction.